We are Ascend NTNU from the Norwegian University of Science and Technology, and since being founded in 2015, we have developed autonomous drone platforms for multiple international competitions. With a proven track record of innovation and dedication, we're now setting our sights on SUAS competition in 2023. The entire development team consists of over 30 students in 5 technical groups: hardware, perception, autonomy, control, and DevOps. In addition, we have our non-technical groups, marketing and business, in charge of recruitment and sponsorship, as well as our board, who manage the whole organization. Our competition team is subdivided in 3 groups: the primary critical mission crew, the backup mission crew, and supporting engineers. Serving as team captain, we have Kristoffer Sunde Mørvik, who's a third-year cybernetics and robotics student. Our safety pilot is Eivind Møen, who's also a third-year cybernetics and robotics student, who's a drone pilot. Our GCS operator is Andreas Utkilden, who is a second-year cybernetics and robotics student. Our autonomy engineer is Bård Wikmark, who is a second-year computer science student. Our perception engineer is Edward Sire, who's a first-year cybernetics and robotics student. One of our hardware engineers is Jørgen Knopf, who is a third-year cybernetics and robotics student. Another hardware engineer is Magnus Cederqvist, who is a first-year mechanical engineering student. And last but not least, our networking engineer, Marius Andreas Arder, who is a communication technology and digital security third-year student. Our latest UAS aims to solve all specified tasks for the SUAS Challenge 2023 and is named Fenrir after the Fenrir wolf of Norse mythology. Fenrir is a heavy-lift carbon fiber hexacopter weighing nearly 25 kilograms when fully loaded. Fenrir is designed, optimized and tested for all challenge scenarios and is ready for the tasks such as autonomous flight, ODLC, air delivery and obstacle avoidance. Based on the SUAS rule set and different criteria for the various scenarios, we've decided on acceptance criteria for the different parts of the challenge, as well as general operational and safety requirements. For the operation scenario, the flight must be safe and robust and maintain maximum score. The ground operators and safety pilots must undergo proper training, ensure the fail-safe system works as intended, and follow operational procedures that will be specified further in the video. For the autonomous flight scenario, the following must be achieved: a flight time where a full range test is done within 30 minutes, a range of up to 20 kilometers with full payload. Waypoints need to be reached within a 7.6 meters diameter circle, and the payload capacity being 2.5 kilograms, while the maximum takeoff weight is 25 kilograms. For the airdrop scenario, we have arrived at the following requirements. We need to fly to the drop zone and deliver the payload, posing no safety risk to people who might be in the area. We need to keep a height of a minimum of 23 meters, where the payload consists of 5 bottles, each being at an 0.5 liter volume. The bottles must remain undamaged throughout the entire delivery scenario, and each bottle must land within 4.57 meters of the marker. We also get extra points for time. To be able to detect the markers where we drop the bottles, our ODLC systems must reliably detect, localize, and classify all standard and emergent objects within the airdrop boundary. Another big competition scenario is the aircraft avoidance, where we need to avoid aircraft collisions throughout the competition. The avoidance algorithm should reliably respond to proximity obstacles on multiple occasions. On top of passive avoidance, it can determine when avoidance is needed using active predictions of potential obstacles. The Fenrir platform consists of 2 parts, one UAS hexacopter and our ground control station. The UAS subsystems include a fine-tuned imaging system that utilizes a high-resolution camera and onboard computer for ODLC, a custom winch lowering mechanism for airdrop, a flight control unit paired with radars for aircraft avoidance, and radio telemetry links for control, and a 4G LTE link for monitoring between Fenrir and the ground control station. Speaking of the ground control station, our GCS setup consists of the following: radio telemetry links for control and 4G for monitoring, and a custom PX4 software framework for the autonomous navigation system. In addition, the ground control system integrates a custom-made waypoint rerouting algorithm that allows the drone to fly within the geofence border autonomously. Our imaging system is built around an Allied Vision Alvium 1800 U-2050C camera, which is used to stream 5K images in up to 21 frames per second at full resolution. The camera pairs with a TechSpec HP lens, increasing the light collection and spatial resolution. The camera and lens are interconnected and attached to an NVIDIA Jetson or an NX onboard computer. The team uses only the camera to capture the images, while the onboard computer processes images to prevent expensive demosaicing and limited FPS for better performance. Object detection utilizes NVIDIA's TensorRT framework as a C++ ROS2 node to maximize inference efficiency and allows for greater model swapping flexibility. For the detection algorithm, we chose YOLO v5 over YOLO v7 due to prioritizing reliability over scalability. A ResNet 50-based object detector subscribes to the camera node and publishes all images containing objects to the classifier. The detector node will send all detected pixels to a ROS2 classification node supported by a modified ResNet 50 neural network model. By default, the convolutional neural network has one fully connected layer, allowing only one object in class to iterate all combinations between object shapes and colors. The resulting sequence will be highly inefficient due to 40,000 varieties of symbols and colors. To resolve this problem for better efficiency, we expanded the ResNet model with 4 parallel layers, distinguishing object shapes, object colors, symbols, and symbol colors. This leaves us a set of pre-established combinations and outputs of 13 different shapes, 10 shape colors, 36 symbols, and 10 symbol colors, adding up to 69 combination outputs to classify. Object localization relies on position data from the built-in INS and a ROS2 filter node. Our strategy is to calculate the location based on approximation. We will use position data from the flight control unit to transform the camera's reference frame into GPS coordinates. After flying with enough GPS coordinates gathered, the filter node will use the image results from the object classifier to transform bounding box points into locational data. By dividing the flight zone into grid cells, the cell containing the detected object will increment based on the detection confidence. Then a Gaussian blur will be applied to the grid, after which we find the probable location by selecting the grid with the highest value. The payload includes 5 pre-attached water bottles, motors, brake pads, and customized winches made of spools of fishing lines. All payload components are attached to Fenrir's underbelly throughout the mission. This allows Fenrir to drop all 5 payloads without restarting the flight. The airdrop mechanism includes 5 lightweight spool-spun systems mounted to linear actuators for each water bottle. Each actuator mount has a built-in encoder system connected to an ESP32 microcontroller with a PD regulator, which directly triggers and controls the speed for dropping the payload. Each water bottle weighs 500 grams, which adds up to 2,500 grams, and an additional 700 grams of the airdrop components must be attached. To trigger the airdrop mechanism, we chose to use serial communication over a ROS node using a PySerial framework. The autonomy command system will first send client information about the water bottles to the ROS node server. Once the server confirms the payload, the ESP unit pushes the brake pad. A PD regulator system controls the speed of the bottle's descent to ensure safe delivery to the specified area. Time, speed, and any occurring feedback will be sent back to the client from the encoder to compare optimal performance. This way, the airdrop operation will be speedy while ensuring the safety of anyone nearby when the payload approaches the ground. Fenrir has an autonomous release mechanism that separates the payload from the drone. A fishing line is mechanically secured to the spool by threading the line into a hole in the spool. The spool is then spun up to the required length of approximately 25 meters and fastened onto the custom bottle mount. At the appropriate height, the line disconnects from the spool due to gravity, reliably separating the payload. The autonomous release mechanism ensures safe and precise payload delivery, allowing the hexacopter to perform the delivery autonomously. Our air-to-ground network solution is based upon a radio telemetry link as our primary communication solution between the GCS and Fenrir. The ground station is directly connected to a telemetry radio powered by an RFD900X modem for transmitting mission-critical information at 900 MHz. The modem is extremely lightweight and compact in design, which can be tightly embedded within our 3D printed shells. With 2 RF links attached vertically as the antenna, the signal strength can reach an extended range of more than 40 kilometers. Likewise, a smaller version of the RFD900X modem is also attached on Fenrir to directly retrieve outbound data from the flight controller unit using a MAVLink. These outbound data mainly consists of Fenrir's location coordinates, height, and attitude. The planned default air data transfer rate is 4 kilobytes per second and can be adjusted to a maximum of 500 kilobytes per second. This guarantees the system is capable of deployment without third-party infrastructure using a 4G connection. However, for ease of use and monitoring purposes, the drone is also equipped with a 4G Telit LE910C4 module. This allows Fenrir to connect to local 4G base stations to send monitoring data during the flight. WireGuard VPN tunnels will encrypt all monitoring data to ensure a secure connection from unwanted activations. Then the encrypted data will be transferred to a ground control station through a RUTX14 router. In North America, the expected frequency is 1900 MHz at the B2 band, 1700 MHz at the B4 band, and 700 MHz at the B12 band. For extended signal range, an R9M long-range radio module is attached to the back of the TX16S radio controller to work at the frequency of 900 MHz. The aircraft is a hexacopter named Fenrir, with 6 motors and propellers attached to the end of the 6 octagon-shaped carbon fiber arms. 3 factors determine this engineering decision: a larger payload capacity, more stability with extra motors, and safety measures to maintain flight when one propeller malfunctions. The main advantage of a hexacopter is more lift-generating surfaces than a quadcopter, which can increase stability and control, especially in windy conditions. The hexacopter's mainframe is constructed from 2 hexagonal carbon fiber plates that cover the top and bottom of the power distribution board. The plates are 6mm thick and sandwiched between 6 45mm M4 standoffs and 12 custom brackets at each corner. The prefabricated brackets are mounted for each drone arm and stabilize the mainframe, resulting in a rigid and lightweight structure that forms the basis of the drone's assembly. The choice of carbon fiber plate material was determined through initial CAD iterations using Autodesk Fusion 360 and eventually chose carbon fiber for its lightweight quality against pressure. Several simulations were run on stress analysis, identifying the most pressurized areas around the plates. The plates were either trimmed or pierced to reduce weight to 1.5 kilograms while maintaining structural integrity. Fenrir's propulsion depends on the Altus X60 Uno system with 6 motors controlled by Alva ESC and 6 28-inch Alva Maeslick propellers. These ironless motors were reported to have high reliability and thrust power and can be easily integrated with our previously present components and systems. With dedicated 3D printing technology, the prefabricated motor mounts are replaced with custom printed ones to reduce additional weight. Furthermore, custom designed PCBs connect the signal wires to each of Fenrir's 6 arms, making them easily detachable by only disconnecting 2 cable connectors. The combined efforts in custom solutions make Fenrir more accessible for transportation and save setup time whenever needed. 4 solid-state lithium-ion Aries 6S 30 amp-hours batteries are installed to supply Fenrir's power needs. With a higher energy density, the expected service life can reach about 25 minutes with all 4 batteries in 12S configuration. Fenrir's autopilot system relies on the PX4 framework and is processed through the onboard computer. Including a customized rerouting algorithm, the PX4 autopilot system can handle all flight scenarios such as waypoint navigation, modified speed modes, and path rerouting. During the prep phase, the ground control station uploads mission coordinates to the Cube Orange, which will then be integrated into 3 unique mission files, including ingress waypoints, search boundaries, and geofence borders. Upon taking off into the air, PX4's autopilot system will switch between 2 PX4 autopilot modes. First, the mission mode will guide Fenrir to fly each waypoint and search area by consecutively processing a set of commands from the onboard computer. During the search phase, these commands work alongside with our ODLC and avoidance systems. Then the command center switches to the offboard mode during the airdrop phase. This allows us to continuously optimize Fenrir's desired position to the drop point precisely and accurately. Once the airdrop completes, flight mode will be switched back to mission mode for continuous autonomous flight between each drop point. Our GCS is a simplified Q ground control interface perfectly compatible with PX4. The main display is a satellite map covering the flight zone. In the center, Fenrir will be marked as a red arrowhead moving along several lines as a connected flight path. The orange-colored line represents the integrated flight path from the mission file, while the red-colored line indicates the current flying path. On the GCS display, a set of manual mode buttons including fly, land, return, and pause will be available in the top left corner. 2 circle icons on the top right corner will display the current altitude and compass angle. In the bottom center, there will be indicators about the current height, speed, time elapsed, and total distance traveled. Then the bottom right corner displays the communication traffic between Fenrir and the ground control station. To ensure Fenrir can operate in an environment with multiple other aircraft, we've implemented an obstacle avoidance algorithm based on the rapidly exploring random tree approach. This allows us to identify points that allow us to perform path adjustments that secure a safe distance from other aircraft. Fenrir's aircraft avoidance algorithm is integrated as a C++ ROS2 aircraft avoidance node to communicate with the PX4 autopilot system and the autonomy command center. The algorithm takes its input from the 7 IWR6843ISK radar modules attached to the drone, 1 on each arm, as well as 1 top-mounted module which ensures good coverage both when hovering and during flight. The algorithm works by regularly scanning the area between Fenrir and its intended destination and sampling a fixed number of points in that area. This includes autonomously generated goals with a distance of less than 5 meters within the fly zone. If the path to the goal is clear, Fenrir will fly directly toward the goal. However, if there are any other aircraft in the way, the algorithm will calculate the cost of travel between Fenrir and each sampled point, and then between each sampled point and the goal. The cost factors taken into account include the travel distance and the distance from other aircraft. Fenrir will then choose the sampled point with the lowest cost, as this should be the most effective and safest path to the goal. If the goal is completely blocked by another aircraft, the algorithm will command stationary until the goal is cleared. The entire avoidance algorithm is designed to interact with the PX4 autopilot system to update the flight plan in 3 phases. First, in the waypoint navigation phase, the aircraft avoidance node will constantly monitor any obstacles in the air and fly straight to the next waypoint after correcting the flight path. In the search phase, the aircraft avoidance node will resume to its previously blocked waypoint after avoiding the obstacle to ensure that all waypoints within the flight zone are appropriately covered. Then, in the airdrop phase, Fenrir will switch from mission mode to PX4's offboard mode. When Fenrir moves above the target marker, the Autonomy Command Center sends post-stamped messages to the aircraft avoidance node. The aircraft avoidance node calculates the coordinates and sends corrections to the PX4 interface for offboard movements. We're quite happy with the Fenrir system now, but while getting to this point, we've considered several other approaches. These were ultimately rejected during our concept review, so here are some ideas that were considered but ended up being discarded. We first considered a VTOL or a quadcopter design for the aircraft. However, we've determined that a VTOL would be too complex regarding design, manufacturing, and transportation, while a quadcopter, while being easier to construct, lacks payload space and redundant propulsion for safety measures. Both designs offered moderate efficiency and speed, but were inferior to the advantages of using a hexacopter for the SUAS mission. Previously, we also had a canopy and a folding mechanism for our arms in place, but those were dropped because of weight issues. When it comes to safety risks and mitigations, we found that design and testing discovers and mitigates risk factors, as well as operational procedures being there to detect possible problems before they happen and ensure safety if a failure occurs. In a sense, people safety is much more important than gear, and all operational decisions that we do reflect that. We've got multiple safety mechanisms installed on our aircraft, amongst others kill switch, a safety pin on the airdrop, and some fail-safes for communication, but in Norway it's actually not allowed to drop bottles just out of the blue, so we're in constant contact with the authorities about what we are allowed to fly, when we're allowed to fly, and we always watch out that people are safe in the vicinity of our enormous drone. In Norway, testing the performance of Fenrir is challenging due to the harsh weather conditions throughout the development cycle. Fortunately, we have developed our own in-house Unity simulator for testing all of our systems in 3D environments that closely resemble what we expect to see in real life. When it comes to ODLC performance, this was mostly tested in our own in-house 3D simulator on over 10,000 images with an average success rate of 97%, a recall score of 98%, and a precision score of 99%. The object classification system can successfully classify objects with an average image resolution of 169 times 169 pixels. For object localization, 420 objects were tested with an average error distance of 6.9 feet. As for the airdrop performance, in real-life testing environments, we have 10 out of 10 successful drops for 22.5 meters, where the fastest landing speed was 4 meters per second and the slowest 2 meters per second. This was when they were regulated to 3.5 and 1.5 meters per second respectively, so it could be slowed down and sped up. All bottles survived. The graph shows a set point at 2 meters per second. With a state machine and modified wind conditions, over 3,600 bottles were successfully dropped with a 90th percentile distance of 1.69 feet. Our network solution was tested in real-life open space with only one parallel stream. The overall data transmission rate hovers between 3 to 10 megabytes per second, but with two parallel streams running simultaneously, one stream can reach a faster rate while another is slightly slower. As for the transmission rate, it's irrelevant since our network is 4G LTE. As per our latest test flight, we've met all flight performance requirements, with flying up to 12.5 miles per flight with a fully loaded weight of 25 kilograms, and over 20 flights with about 90 minutes in total. In addition, we've flown a testing drone with attached subsystems for 60 minutes. Error estimation between waypoints is configurable with a max waypoint error of 6 feet. The multi-rotor structures allow us to have a lower turn radius of less than 1 foot, and as for the height, we reached 300 feet with a vertical takeoff. Fenrir's autopilot system also works flawlessly as we conduct in real-life testing. With 7 autonomous flights and an average flight distance of 28 kilometers, we've attempted and correctly hit 66 out of 66 waypoints with an error margin of about 1.01 meters per waypoint. As for the obstacle avoidance, most tests here were done in the simulator, again with 2 competitor drones flying at the same height as Fenrir around the marker area. The average number of maneuvers while searching the area is about 12, with a success rate of 98%.
Jeg er klar. Jeg filmer.
In this video, we've described our UAS system Fenrir and its ground station for mission control. We've introduced you to our dev team and our competition team. We've covered the requirements derived from the rules and targets of the competition and presented our solutions for handling these different challenges. This includes dozens of technical solutions and essential operational procedures and principles for ensuring that we fly safely while hitting our performance targets. Then, importantly, we've also gathered the numbers and necessary documentation to show you that we haven't just made some pretty slides with technical jargon. We have in fact created a fully functional UAS system that flies safely, as demonstrated by our proof of safe flight and relevant performance metrics. We are very proud of our achievement and have learned an enormous amount about what it takes to create complex systems. We have worked hard, collaborated across disciplines, and grown as a team. Now we look forward to seeing what other teams have come up with and to compete against them after our exams. We are Ascend NTNU. Thank you for your attention.